resources available, an infinite amount of food and space, well, and that none of them die, so you're oversimplifying it. But the simplest population growth model, and you can do this for short term. For long term, it eventually becomes a problem, but for short term, relatively isolated populations with a large amount of resources in comparison to the number of beings there, an exponential model works for the short term. So a good example would be a single bacterium you stick in a petri dish at time t equals 0, and then you wait. Now, after a certain amount of time, the number of bacteria are going to double. So if you start off with one bacterium, this time you'll have a positive constant, e to the kt. Now, this isn't a perfectly accurate model. K would be a number which depends upon the rate at which bacteria divide. Every time a bacterium divides, it creates 2 daughters. So you'd start off with 1, and after a certain amount of time it would divide and produce 2, and after a certain amount of time each of those would divide and produce 4. Now, this isn't a perfect model, and there's a certain reason why. It's because this function here is what we call continuous, and the number of bacteria in a petri dish is what we would call discrete. Now, what continuous means is that in terms of limits, I'm going to define continuity in terms of limits in a little while. But what continuity means intuitively is a function is continuous if you can draw it without ever having to lift up your pen from the paper. You can draw the shape of the function f of x without ever having to lift up your pen. Intuitively, it essentially means that there's no breaks or there's no breaks in it at all. It's completely connected everywhere. Now, there's a more strict definition of continuity that's important mathematically and important otherwise in semi-mathematical fields like physics, and I will get to it in a little bit. But essentially, that's the intuitive definition. Now, bacteria aren't like that. You don't have 2/3 of a bacterium. You either have a full bacterium or you don't. It'd be like going into a room in a classroom at a school and counting the number of computers in the room. You don't have 2/3 of a computer. You either have a computer or you don't. It's a binary value. So in some sense, this is somewhat of an accurate model for population growth, but there are limitations, and that's one of them. But essentially, what it's going to look like, and this is one thing I want to stress, how models are not, especially models like this, shouldn't be taken too literally. There's some debate in physics right now about whether quantum theory represents actual reality or represents a model that produces predictions that are accurate. And that's a raging debate right now in physics. In fact, it's been a debate for a long while. But essentially, the idea is you don't necessarily take every model completely literally. And this model, you can't take completely literally. This is a model. This is a simplification. It's useful for predictions, essentially. It can give you an approximate number. But if you get like 2500.6 bacteria, you're getting a relatively close value to what you would expect the number of bacteria in the petri dish to be. You're probably not going to look out this far anyway. You probably don't care out to that many decimal places. If you're already around 2500, whether it's 2500, 2501, or 4000 or 2499, that doesn't really matter. So that's part of the reason why we can do this. It's just like technically the electrical charge on objects is not continuous. The smallest unit of charge that can exist independently, not the smallest unit of charge that can actually exist, but the smallest unit of charge that can exist independently is the amount of charge in an electron. And it can be either positive or negative. On an electron, it's negative. On a positron, which is the antimatter twin of an electron, it's a positive charge. But the smallest quantity of charge, the smallest amount of electric charge that can exist is the amount on an electron. The smallest amount that it could exist independently. So that means technically the charge on all objects on a macro scale is technically not continuous. But when we do classical electrodynamics, we assume that it is continuous, for the simple reason that a charge on an electron is so insanely small compared to the charges that we usually deal with that it's not really going to factor into the calculations. Like, if you have a calculation, you might have 5, 6, 2, 3, blah, 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 blah. And the fact that it's technically a discrete variable might factor in way out here in like the 9th or 10th decimal place. Well, most physics apparati can't even measure values out to this far in the decimal places, especially classical equipment that would have been used in, say, the 1800s when classical electrodynamics was around. So if this is how you know when to use what model. If adding extra complexity to your model doesn't change the value of your computations in a way that can be measured, then adding extra complexity, while technically more accurate, is not necessary or useful. That's why we can use Newtonian physics to send people to the moon, even though relativity and quantum theory are more accurate. They're unnecessary. They're adding extra degrees of complexity. The calculations, the value of the calculations would technically change, but not to an amount that could be measured. Not to an amount that we could measure in terms of the trajectory that we would assign a NASA space shuttle. So this is how you know what models to use. If a model accurately describes a phenomenon out to the point at which things can be measured, then it is okay to use that. That's how you know when you can use simplifying models. So anyway, that little distraction aside, what this is going to do is at time t equals 0, you're going to start with 1, because I said you're starting with 1 bacteria that you're sticking in the petri dish. And then over time, it's going to grow like this. It's going to just shoot off and grow at an increasing rate. Now, it turns out that exponential growth outstrips any polynomial growth. Exponential growth outstrips any polynomial growth. Now, one reason for this is that, remember I said there were many definitions for the value of e. The function e to the x, and this is later once we get into the idea of infinite series, e to the x can be defined as 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120 plus blah, 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 forever and ever. So you can obviously see x squared, x cubed, x to the 4th, x to the 5th. Any power, any integer power of x is going to be in the series for e to the x. Now these coefficients here, they come into play because of Taylor's theorem, but I don't really feel like getting into that. But essentially what this series shows, you're going to be adding terms out here farther and farther. Remember, things start to behave like their largest power of x. Polynomials behave like their largest power of x. Well, e to the x is essentially an infinite degree polynomial. The coefficients down here tend to grow faster than the powers grow. So it doesn't cause a problem as the power gets infinitely large, because these coefficients down here grow even faster. But essentially, it behaves somewhat like an infinite degree polynomial. And so any polynomial of finite degree, you can take this out to a further degree. You can take this out to a higher power. And so exponential growth always outstrips polynomial growth. So what does that mean? That means if you have the limit as x approaches infinity of x to the 287,000th power over e to the x, you get 0. It's 0. And the reason why it's 0 is because you can take e to the x out to the 200, you can take the series for e to the x out to the 280